In question number 15, the graph of g prime is shown. So this is the derivative function, and the g consists in the derivative function of g. So it's a semicircle and this triangle here. And we're being asked to evaluate g of 3. That means we need to generate a function g based on the derivative. Well, that means we need to use the area. And we know that the displacement of this g prime function represents the change in the g, but to get the actual g value, we need to have a starting point. And our starting point is going to be this point here. Okay, so when we set up this function, g function, I'm going to say g of x is equal to, well, we need some starting point, and we need the area under the curve from the starting point, and we're going to generalize the endpoint as x, and it's going to be under the g prime function, and we'll write it like this. We just change the variable to t. So we need the starting point. That starting point is where we're going to start to integrate, is from 0. That's going to be our starting point. And our starting y coordinate then, for the area under from 0 to 0 will be 0. So this is going to be our starting point of 0 area displacement. And we're going to start at a y value of 1. So this is important to make sure that we understand how to set that up. Once we set that up, okay, we want to find g of 3. Okay, so g of 3 must be equal to 1 plus the area under the curve from the starting point, 0, all the way to x is equal to 3. So it's going to be plus that area there. Maybe I'll do this in a slightly different color so that we can differentiate the different parts of this problem. So the area under the curve here is going to help me define the displacement from 1. Okay, and that's going to be from 0 to 3 under the g prime function. Okay, so then I want to then work out that value, that area. That area is going to be the semicircle. So this is a circle of radius 2, so 2 squared pi over 4. Well, that area just works out to be pi. This is a triangle, 2 times 1 divided by 2. That area works out to be 1, so this is going to be pi plus 1. Now be careful with this answer, because if we don't account for that starting point, we get this answer, which is wrong. Okay, so we want to make sure that we do this, we account for that starting point, and when we do that, we end up with the answer of pi plus 2. The answer is B. Okay, so this next question, we're given a polynomial function, and we're asked to find the maximum value on this interval. This is a polynomial function. We know that it's smooth and continuous. We can differentiate it. We should have some polynomial that looks kind of like that. Okay, so we want the derivative. So f prime of x is equal to 3x minus 12, x squared minus 12x minus 15. And we want to test for maximums. Maximums can occur. They can occur when the derivative is equal to 0. So we're going to solve this equation equal to 0. We'll factor this. So this factors, and we get solutions of, it's going to be plus 1, x plus 1, x minus 5 equals 0. So we're going to have 0 slopes at negative 1. And it's potentially that point there. And x equals 5, which is potentially that point there. Okay, so we have a potential test point. When I do my slope chart, I have negative 1, and it's going to look like this. My derivative f prime at -2. When I plug -2 into this, I get negative, negative, that's positive, so it's going up. So yeah, it looks what I've drawn there. F prime at 0 equals negative, so it's going to go down to here. And then at 5, there's another 0. F prime at 6 is equal to positive, so it's going to go up like that. Okay, so that's what my slope charts look like. However, remember that you have to account for this interval of 0 to 6. So this is outside of the interval. Okay, and so we need to test in this interval for min and max. So we are in this case really just the max. And when we do that, we need to test our endpoints and critical points. So I'm going to put the -1 on the outside, and we can calculate it. Plugging in -1, I get -1 minus 7, or minus 6 is -7, plus 15 is 8. Okay, however, we cannot use that as part of our candidates. So I'm just going to make sure this is not a candidate because it's outside the domain. Okay, so that's not a candidate. We're going to test, the only other candidates then are going to be 0 and 6. And well, I guess I could put in 5 as well. Okay, but we know 5 is a min. So when I calculate f of 0, plugging in 0 into my function, I get 0. F of 5, when I plug in 5, which I don't really need to do, but it's going to be 125 minus 150. So that's going to be -25 minus 75. So it looks like it's -100. Okay, so that would be our min point down here. The other endpoint, when we plug in x is 6, we get 6 cubed minus 6 cubed minus 15 times 6, or -90. Okay, so this is actually not a very good chart here, but we're going to end up with, these are our candidates. We know that then this must be my absolute max. So this is a maximum that represents my max. So the maximum value of f, again, make sure that we're looking at the f values and not the x values, but the maximum value occurs at 0. X is 0, the maximum value is 0.